Let's assume that we have a linear transformation from a vector space V into a vector space W. Let's suppose that this transformation is injective and surjective. Then in particular, the dimension of these two vector spaces must be the same. Let's suppose that we have a basis V1 equal to V1 Vn and a basis V2 for W equal to W1 Wn. Then we will explain how to compute the inverse of this transformation. Then what we do is we find the matrix associated with this transformation with respect to these two bases. And just to remind you, what is this? The first column of A, we write down the coordinates with respect to these bases of T of B1. Remember that here is B1. T of B1 is an element here, and since it is an element here, I can write the coordinates with respect to these bases. I just write this vector as a linear combination of this, and the weights are what I write down here. And the last column are just the coordinates with respect to these bases of the vector T of Bn. Since this transformation is injective and surjective, then this matrix is invertible. And then we can just do a procedure here and compute the inverse, A inverse. And then we have that the inverse of this transformation, T inverse, that goes from W into V, the matrix associated with the basis B2 here and the basis B1 of this transformation is just this matrix. And then we can somehow find a formula using the fact that this is the matrix of this transformation. Let's do an example to illustrate this. Let's see if I can fit that example here. Let's suppose that we have the space S22, which is the space of symmetric matrices 2 by 2. They are of the form A, B, B, C, right? Such that A, B, and C are complex numbers. Then this is a three-dimensional vector space, and for this vector space we can take the bases 1, 0, 0, 0, 0, 1, 1, 0, and 0, 0, 0, 1. This is a basis for this space. And let's suppose that we have the transformation T from the vector space of polynomials of order 2 or less into S22. And let's suppose that this transformation takes a polynomial P and is sent to P of 0, P of 1, P of 1, and P of 2. Notice that this transformation, it goes to the space of symmetric matrices because these two entries are the same as required. Let me just say that if P is equal to A plus Bx plus Cx squared, then T of P would be P of 0, it would be just A. P of 1 would be A plus B plus C. P of 1 is A plus B plus C. And P of 2 is A plus 2B plus 4C. We can check that this transformation is injective and is surjective, then it has an inverse. Let's compute the inverse. Then what we do is we pick a basis for the domain. Let's suppose that we take B2, sorry, let's call this B1 because this is the domain. B1 equal to the polynomials 1, x, and x squared. And let's call this B2. Then we need to compute the matrix related, the matrix associated with this transformation with respect to these two bases. And then what we do is we compute, to compute the first column, we evaluate T of B1. Remember, this is B1, B2, and B3, just as here. This is going to be W1, W2, W3, and T of B1 is just T of 1, and then you will get 1, 1, 1, 1, and this is just, you can see easily that this is just W1 plus W2 plus W3, and therefore the first column of A is going to be equal to the vector 1, 1, 1. Let's compute T of B2. Where can I do that? T of B2, let me do it here. T of B2 would be, T of B2 is T of the polynomial x, and T of the polynomial x is that polynomial evaluated as 0, which is 0. We can say here T of x, A is 0, B is 1, and C is 0. Then we have 0, 1, 1, and 2. How do we write this matrix as a linear combination of these three? It's just W2 plus 2 W3. What are the weights? So that we can find the coordinates. The weights are 0, 1, and 2. 0, 1, and 2. Now let's compute T of B squared. To compute T of B squared, which is T of the polynomial B3, is T of x squared. We get the matrix 0, 1, 1, and 4. And this is just W2, this matrix, plus 4 times W3. And then we have the coordinates 0, 1, and 4. These are the coordinates with respect of this matrix with respect to that basis. And then this is our matrix A. Then we compute the inverse. We can do one of the procedures to compute the inverse. Remember, one of them is just to write that matrix 1, 0, 0, 1, 1, 1, 1, 2, 4, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. We find the row reduced echelon form of this, and then we will get here the identity. And here we will get 1, 0, 0, negative 3 half, 2, negative 1 half, 1 half, negative 1, 1 half. That means that A inverse is 1, 0, 0, negative 3 half, 2, negative 1 half, and 1 half, negative 1, 1 half. Now let's see how do we use this to compute the inverse of T. T inverse will take a matrix. Let me just to differentiate, let's call this A, B, C, and here let's call this symmetric matrices like A, B, C, D, E, E, F, right? Such that D, E, and F are complex numbers. The inverse will take D, W1 plus E, W2 plus F, W3 into let's see what is A inverse applied to D, E, and F. This is just D. Here we have a negative 3/2 D plus 2E minus 1/2 of F, and here is 1/2 of D minus E plus 1/2 of F. Then these are the weights of the answer. That means that this is sent into D times 1 plus negative 3/2 D plus 2E minus 1/2 of F of X plus 1/2 of D minus E plus 1/2 of F times X squared. Now we have the inverse transformation. T inverse goes from the space S22 into polynomials of degree 2 or less, and T inverse of, when you think about DW1 plus EW2 plus FW3, you are thinking about this matrix. D, E, E, F. It takes this matrix into this polynomial. D plus, let me just rewrite it, negative 3/2 D plus 2E minus 1/2 F times X plus one-half D minus E plus 1/2 of F times X squared. Okay, notice that we have used this. We have first find the matrix of the transformation, which is this. We have computed the inverse, and we have used the inverse to find a formula for the inverse of the transformation that we started with. Let's do another example. Let's consider the transformation T from P1, polynomials of degree 1 or less, into C2. And let's suppose that this transformation takes A plus Bx into the complex number A plus B, B minus A. Then to compute the inverse, we can check that this is injective and surjective. Then we pick a basis for these two spaces. Any basis will work, but the easiest the basis, the better is the way to find the inverse. Then for P1, we're going to pick this basis B1 equal to 1 and X. And for C2, we're going to pick the bases E1 and E2, which are the vectors 1, 0 and 0, 1. Then to compute the matrix of the transformation, we need to compute T of V1. This is V1, V2, W1, W2. And T of V1 is just T of 1. And T of 1 is A equal 1 and B equal 0. Is the vector 1, negative 1. And we can see that this is just 1 times E1 minus E2, and that means that the first column of A is this 1, negative 1, because these are the weights. T of B2 is just T of X, and for T of X, when you think about the polynomial X, A is 0, B is 1, then you get the vector 1, 1, and this is just 1 times E1 plus 1 times E2, and then the weights, which is the second column here, is just 1, 1. To compute the inverse of this matrix, we know that the inverse A, B, C, D inverse is 1 over the determinant of the matrix AD minus BC, and then we switch these two, D and A, and we change the sign of these two. Then we get that the inverse is 1 over the determinant. 1 minus -1 is just 1 plus 1, which is 2. And here we switch these two, and we get 1 and 1, and we change the sign of these two. And we get 1 and -1. This is the inverse. Now let's see what is the inverse evaluated at some point CD. Right? Let's use here for this, let's use A and B, and for this one, let's use C and D. Like, just to, let's use for elements in P1, let's use it like A plus BX, and for elements in C2, let's use C and D. Then this is just 1/2 of 1, -1, 1, 1 times CD, and this is just 1/2 of C minus 1/2 of D, and 1/2 of C plus 1/2 of D. And therefore, the inverse transformation, it goes from C2 into polynomials of order 1 or less, and the inverse takes CE1 plus DE2. Just do the linear combination of the bases, which is just T inverse of CD, and it's sended to, you need to use these weights and these bases. Then you will get 1/2 of C minus 1/2 of D times 1 plus 1/2 of Z plus 1/2 of D times X. It takes an element in C2 and send it to a polynomial.